Alright, before we start, I'll recommend you to watch these videos first. If you are done, let's get into it. Recall that in previous videos, we found that the four equations that explain electric and magnetic fields, which this side is universal and this side is for non-accelerating frame or non-accelerating charge. And by Helmholtz theorem before, the electric field can be explained as scalar potential as this Poisson differential equation, and then for magnetic field, we will see that this set of equations for magnetic field clearly tell us that this vector field is purely curl or solenoidal. So then I can define the P as curl of some A vector field, which this create magnetic field as solenoid vector field. Helmholtz theorem comes from condition of no divergence and the curl itself has something as such. And by using the curl equation here, we will get this, and notice that we can choose here nabla.A is equals to 0, which it still satisfies these all conditions, which will be our discussion in another video. And the result for all them as this. Then we have A vector as vector potential and V as scalar potential, or we summarize as electromagnetic potential. Next, as we know in previous video, the Coulomb force affected to Q charge as this, which here, if we have this interaction to charged particles by electric field, then we have this set of equations because of the third law of motion. But here, after we know about magnetic field, what kind of force that caused by magnetic field? Of course, in previous video, we know the system of magnetic field along a wire that has G capital current density, which here, the force will give you additional force despite electric Coulomb force as this direction analog to magnet force. If we have two magnets here that combine as N and S pole as this, by unified system, we will get the new magnet as this, which the attraction force will be like this as attracting or repelling. So by this system consequence, we will get this cross product completion as J here, which here J is electric current differ from J capital here as electric current density. If these two forces combine or coexist, then the total force will equals to this, or the force density will equals to this, usually known as Lorentz electromagnetic force, or sometimes we call it Lorentz force or just electromagnetic force. But now the question is what we get from this. In previous videos, we know that the electric phenomena such as electric current can create a magnet which developed in 80 and 20, but now can a magnet create electric phenomenon? This question was solved in 1831 by a scientist named as Michael Faraday and then formulated mathematically by Lenz. In the result of Faraday experiment, he stated that magnet can create electric phenomenon if the magnet move forward to electric wire loop or move backward from it. Second scenario, area of loop change a long time, or the last scenario, magnetic strength through the loop change a long time, which then Lenz formulated it that the total energy over all single one charge here is equals to minus of the rate of change along time for the flux of magnetic field that passing through the area that enclosed by the electric loop, which flux here we have defined it in previous video, and the energy here relate to work energy theorem. First, from definition of flux like this integral, which means that if we have this area and the magnetic field, then this flux tell us about how many arrow of magnetic field passing through the surface. And the next one, by energy work theorem, is equals to this counter integral along L, which is L is trajectory along the loop for the electric current, which if we take small partition of charge, we will get that infinitesimal part of work here is equals to this. So the first derivative of work with respect to charge here is equals to this. Here, this what we want, and the detail of this is for the next videos. So the equality will become as this, and notice that this area or interval of integration here may be time dependent. So let's focus on the flux part. For the first part, we remember that the divergenceless or solenoidal property of magnetic vector field here, which result in this differential form and this integral, and in our system we can use this enclosed volume by some surface as A1, A2, and A3 here, with the magnetic field passing through this surface. And here we can see that this enclosed area may be changed a long time because of this part equation universality. Or here by the integral form we can see that the total flux is equals to 0. So here we can see that the total flux rate of change a long time here of course is equals to 0, which by this we can use the definition of limit by time parameter here like this, which prime here relate to plus h of or shifting by h parameter in time parameter. And next, we need transformation from here to here using Jacobian transformation as this that came from multilinearity of determinant from of course coordinate transform. So then we get m as this, and then we get this, which come from linearization and this h infinitesimal shift. And after that, we get this. And notice that this part here is a component from velocity of total body region movement. And if you look closely, this form creates the divergence of this velocity vector. So by using m, we will get the transformation for dv prime as this, and then take a look that this part create this differentiation, and the other multiplication distribution we will get this limit, and applying limit we will get this. So the next result is this. Here, this part is total differentiation of nabla.p with respect to time. So by partial differentiation chain rule, we will get this. And in this part, we get directional derivative analogy. And in the next result, we will get this part as consequence of product rule for vector calculus. And the result as this. Here, the result known as Reynolds transport theorem, which explains from flux that region of integration change along the parameter. Using divergence theorem in this part, we will get the simpler result as this, which again is equals to 0, and I said this simpler because this part, we know that by the divergenceless of magnetic vector field along A, we will get the same result as divergence of magnetic field is equals to 0. So this part is equals to 0. And here, notice that the partial differentiation with respect to time is commutative, so we can switch the order of the derivative such the nabla here only differentiate for spatial and the t here only differentiate on t, so we get the result as this by using divergence theorem again. And finally, back to our surface before. Here, the total surface which equals to 0 is a linear combination of integral along A1 surface and then A2 surface and then A3 surface. And here I took A3 as small as possible, which I squeeze this area as small as possible, of course, that let the A3 integral here approach to 0. So here we get that A1 area has same magnitude as A2 area but in different direction, which lead this equation is equals to 0. And the conclusion, we get that the flux rate of change along time is equals to this, which I remind you that this integral here relate to rate of change of flux only along A2 or A1. By the result before, we will get this equality, and in the left hand side integral here we see that dl and velocity parallel, so it's equals to 0, which we can see in the loop here. The direction of dl is this, and here the direction of the velocity which represent the electric current. And finally, we get this equation as this integral equation as Faraday-Lenz electromagnetic induction law, which electro belong to this side and the magnetic belong to this side, and has other form as this, which is differential form from Faraday-Lenz electromagnetic induction law. In this result, we will see that for electrostatic, which condition with a magnetic field, or magnetostatic, which rate of change of magnetic field with respect to time lead to zero factor that lead us to nabla cross A is equals to zero factor, which relate to previous videos. And in the end, this equation tell us that magnet can create an electric phenomenon. And that's the very long journey making videos about Faraday-Lenz electromagnetic induction law. I hope you enjoy this video. If you like this video, don't forget to share and subscribe. If you have any question, just drop the comment below. And thank you. See you later.